So now that we've seen bond polarity, we are going to talk about molecular polarity. The idea that, okay, we can figure out if bonds are polar or not. And that's great. That comes in handy in reactivities. But the real property of simple molecules is not just given by bond polarity. For larger molecules which are not diatomic, it's actually given by molecule polarity, not bond polarity. Things like, for example, a basic idea like CO2. Now, CO2 has this particular structure, CO2. And in CO2, if you focus on each of the two bonds, each bond is polar, and highlight the bond here. Each of the two bonds in this molecule should be polar, because O is more electronegative and C is not as much. So O should be negative and C should be positive. But then if I focus on the other bond has the same problem. O is more negative than C. So between the two, which is the negative guy? It's O. And you might say, well, why not this should become 2 plus? But remember, the delta plus and minus are not exactly charges. They are partial charge in terms of quality. So we don't talk about the actual magnitude of charge. We'll just say, hey, between O and C, O is the negative one. Between C and O, O is the negative one. So O's are the negative ones and C is the positive one. Here's an example of a molecule having two polar bonds. This is a polar bond. So is this a polar bond. It is absolutely true. Both of these bonds are polar. So in this molecule, you have a polar bond. And for example, what's happening is that the right O is pulling the electrons towards itself, and the left O is also pulling the electrons towards itself away from C. So the left O is pulling the electrons towards itself, the right O is pulling the electrons towards itself, the shared electrons. So these 4 electrons, because it's a double bond, are more towards the right O. These 4 electrons are more towards the left O. Now, and we talked about each bond being polar. But what is really mattering in the real world is how does the molecule fare out. Looking at the molecule as a whole, if I was treating this like an oval, like instead of not seeing the CO2 as CO2, but something of this nature, let me just draw that. If I was thinking of CO2 like this, as a whole molecule, and the two ends are O's and the middle end is carbon, what I end up seeing is that the two ends have the same partial negative charge because they are identical oxygens, meaning there are as many electrons on the right hand side as on the left hand side. Maybe by using a marker, I can show that this side has a lot of electrons and this side has a lot of electrons, because this guy pulled electrons away from carbon and so did this guy. In the end, these two are fighting for electrons from carbon, right? Which means this side of the molecule has a polar bond and this side of the molecule has a polar bond. Here, this oval represents the overall cloud of this CO2. So when I look at the electron cloud of CO2, I'll see there's electron density here, there's electron density here, and there's less electron density here. And this should be talking about now the overall molecular polarity. And when I see this, what I tend to now look at is that, hey, what I'm showing you right now is this molecule has, for this molecule, this has electron distribution. For this overall molecule, distribution is, it's symmetrical. If you're thinking, it's symmetrical. So for the molecule, overall molecule, the electron distribution is symmetrical. What that means is one end of the molecule is exactly the same as the other end. And because it's symmetrical, we say it is non-polar. You know why? Because basically what's happening is because it's asymmetrical, we say its dipoles cancel out. which means that there is no difference in electron distribution between the two ends. That's what it means by cancelling out, which means it has what we technically say this has no overall dipole. And I need some space, so I'll just scroll right here. This has no overall dipole. Okay, which means this is a non-polar molecule. All right. Yup. That's what's happening here. Let me show you some more examples of this, by the way. I'll give you another molecule. If you remember AlCl3 or even BF3, if you take BF3 or AlCl3, it has 3 single bonds. So let me make BF3 right here. Now, the BF3 bonds are polar. Each individual bond is polar, meaning that in BF3, this is where the electron is moving towards. In this BF3, the electrons are moving towards fluorine. In the leftmost BF3, the electrons are moved towards fluorine. So all 3 bonds are polar. And it results in all 3 ends of fluorine being delta negative. But they are all identical elements, so they all have identical amounts of charge. And the center B, whose charge we don't really care about, it's in the center, that's why, it has a plus charge. Now here's an example of a molecule, has 3 polar bonds, but because the 3 ends of the molecule are identical, it's a regular shape, and all the ends are identical, we say this guy has no overall dipole. We say its dipoles cancel out, which makes this a non-polar molecule. So you're going to have a lot of molecules where the bonds are polar, but the molecule is not polar. Another example, and this is sometimes difficult for people to understand, is that when you have a tetrahedral molecule like C with 4 Cls. So if I take that CCl, then CH4, that's tetrahedral. You know, this is that. Now tetrahedral, remember, is in 3 dimensions, that is exactly symmetrical. That's what this shape is made. You might not be able to know or recognize it, but in a 3 dimensions, a tetrahedral is a symmetrical shape. Shape is symmetrical. It's like the 2-dimensional version of 3-dimensional tetrahedral is like a square, like a cross, like a plus sign, which will be symmetrical, but that would be in 2 dimensions. In 3 dimensions, that would result in tetrahedral layout. And in this tetrahedral layout, all the chlorines are pulling electrons towards themselves like that, you know. And they're all 4 equal elements, so they all 4 pull the electrons equally away from carbon. So they all 4 get a negative charge and carbon gets a plus charge. So each of these bonds are polar, but if I look at the overall molecule, all the 4 ends, it's the ends that matter, guys. It's the ends. So end, 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 edge, end. You know, like the corners. The corners of these molecules are identical. Here also, we'd say the exact same thing. What would we say? That this has no overall dipole. And why doesn't it have no overall dipole? Because the dipoles, we can say, cancelled out. The dipoles cancelled out, which makes this molecule also non-polar. Now, in what scenario would this have been polar? Maybe I should show that to you and you might recognize the difference. In the scenario that if instead of CCl4 is still tetrahedral, but the 4 ends are not the same. Let's say 3 of the 4 ends are chlorine and 1 end is, let's say, hydrogen. You know? And so when I look at this molecule, it seems like, hey, the same shape, but there's one difference. One of the 4 corners is not the same electronegative element. So yes, the 3 chlorines are pulling the electrons towards themselves, and which will result in the 3 chlorines being negative. but this fourth hydrogen is not going to be negative. It will be less negative than these guys. So it's going to give away electrons. It's not electronegative. So in addition to carbon, even this hydrogen will be positive, because relative to chlorine, hydrogen is less electronegative. Here, the 4 chlorines were the same element, so they were equally electronegative. Here, the electrons tend to go down towards chlorine and away from hydrogen. So here, there is a push of electron downwards. Overall, you could say for this molecule, the electrons are being pushed downwards. This represents the overall dipole of the molecule. This is the overall dipole of this molecule. So the right hand molecule, which is CHCl3, that fellow is what we call, it has an overall dipole. And if something has an overall dipole, we say it is an asymmetrical electron cloud distribution, which means it is a polar molecule. And for us, it's important to identify polar molecules versus non-polar molecules, because the properties will differ because they're polar versus non-polar. So here is, this molecule is polar versus these guys that are non-polar. Now, just to throw in a bit of a wrench also, if somebody said, okay, what if instead of H, I'd have an F? Yeah? So Cl, Cl, Cl are there, but now I have another electronegative element, that is F, which is in fact more electronegative than the 3 Cls, right? So now when even the bonds are electronegative, but as far as the overall molecule is concerned, which end is the most electronegative? In these cases, the bottom 3 were more electronegative than the top. Here, the top 1 guy is individually more electronegative than any of the 3 other corners. And remember, these are 4 exactly identical corners. It's not like the top is equal to the bottom 3. They're all 4 identical corners. Just one happens to have fluorine, the other 3 chlorine. So between these guys, since fluorine is in fact the most electronegative element, it'll tend to pull electrons the most towards itself, even away from chlorine, even if there are 3 chlorines, because each chlorine is independent of the other chlorine. And in the right hand molecule, what you will see is that the dipoles will actually point upwards. That's what the dipole will look like. Okay, like that. And the top of the molecule will in fact be negative, while relative to fluorine, chlorines would have to be positive, because chlorines are less electronegative than fluorine is. So these 2 molecules are polar. The direction of the polarity changes. The more electronegative element in the left case is chlorine, but the more electronegative on the right case is on fluorine. But both of these molecules have an overall dipole. They are asymmetrical, and therefore they are polar molecules, while the molecule on the left is non-polar. And what you realize is most important is not that where is the dipole, but which molecule is polar, which is not, because that'll have more real world implications. So it's important for us to know that these 2 guys will be polar, while this guy will be non-polar.